Okay, welcome back everyone. And so we have covered quite a bit of ground, right? In the last few classes, we have been discussing about the Reynolds transport theorem and the integral approach to control volumes. And when we were discussing the Reynolds transport theorem, those were meant for finite control volumes. Then later on, we went to the infinitesimal control volume as well, and then we started looking at how the equations change a little bit, how from the integral equation we move into the partial differential equations for the infinitesimal control volumes. And so that has gotten us quite far. So we have looked at the continuity equation, and then we want to obviously go to the next logical step, which is, well, the conservation of linear momentum, right? Now, to discuss conservation of linear momentum, we have to be able to discuss something called the stress and the strain tensor. Okay, and that's what we are going to discuss. We had already started on this a little bit in the last class. So today I think I would want to elaborate much more on this idea of the strain tensor, and we'll see why it is a tensor as well. But first and foremost, see, we always want to understand where we are with respect to dynamics. Okay, now in Newtonian dynamics, okay, so in Newtonian dynamics, we were concerned with a vector equation, F equal to ma, and this is true for a body, right? So here it's a point body. And we were essentially concerned with this fundamental truth of mechanics, which is that mechanics in a way is keeping tab on the displacement of a body. And you have to define what you mean by body, and you have to clarify that. So when you are talking about dynamics, we are talking about force, we are talking about the acceleration of a point body, and that there is a force which is responsible for that particular acceleration. Now when we come to solid or fluid mechanics, so this is Newtonian dynamics, but the moment we come to the solid and fluid mechanics, our equations change. Okay, and instead we do not encounter forces so much anymore. Instead, what we do encounter are equations like this. For example, this is what you will see in solid mechanics, right? This is stress related to some modulus, and this is strain. And when we come to fluid mechanics, sorry, the wrong equation. We will see that our equations will reduce to something like this. Okay. So there are a few important things here. One is the way we are looking at displacement changes. Here we are looking at the displacement of a body. So we are just interested in understanding how a body is moving in time and space, right? Here, on the other hand, we are now interested in deformation of a body. Right. So you have a body, so this is some body, and this is a finite body now. It's not a point body like the Newtonian dynamics, and this body is not infinitely rigid. So this is going to change in shape. Okay. So this is body at time t, and this is some t plus some delta t. So here now deformation occurs. Which means that the points inside the body are displacing with respect to each other. So how you are going to keep a tab on this displacement is now going to change in fluid and solid mechanics. And in solid mechanics, we are mostly concerned with displacement, which is epsilon. I mean, it's a form of displacement. So if you remember the very simplistic idea, we used to define epsilon as delta L by L, if you remember. Okay, but this is obviously a very simplistic idea because it's a scalar quantity right now, and this stress, I mean here I have not done anything to it, so I have not drawn a bar. So the question is, if force is a vector, what is stress? Is stress automatically a vector? Well, no. We'll see that strain is a tensor. Actually, we will not look at strain, we will look at the strain rate. But in solid mechanics, you come up with strain, which is a tensor, and this quantity equivalently now also becomes a tensor. So this is your stress and this is your strain. In fluid mechanics, we will be looking at strain rate. So we are interested in this form. By the way, this is also a very simplified form. Okay, this is not the exactly correct form, but I'm writing it for a particular reason, because I wanted to draw the analogy with solid mechanics. Now, the important difference between fluid and solid mechanics is solid mechanics has a bindi, and that's what there's a rate here. It's an Indian. Fluid mechanics is an Indian. Well, I'm joking, of course, but this is a good mnemonic, because in fluid mechanics we will be dealing with rates, displacement rates, rather than displacements themselves. So we are not going to be dealing with displacements, but rather with rates. And this will obviously in the next part of our discussion, where we look at volumetric, dilation rate, etc., we will come to that. And we will see that this is actually becomes a tensor. This is also a tensor. In normal solid mechanics, this quantity E, which is a modulus, is a scalar, which it need not be. This is a tensor, this is a tensor. In the most generic case, this can be another tensor which relates two tensors. And then this becomes even higher order tensor. It's called a 4 tensor in mechanics. But often this, for isotropic cases, we can just think of it as a simple modulus actually. Okay, so our basic point is that we now have to keep a tab on deformation inside the body itself. Right? So if you have a small element, okay, so I said our basic idea is deformation. So you have a body, and you have this body at a different time. This is at time t, this is t plus delta t, okay, and we have this small window in here. Let's say this is a packet of particles, and now here it has changed, right? It has undergone some deformation. Now if I were to ask you to keep two constraints, one of which is that the deformation should occur such that the deformed material is still in the plane of paper. So if you are talking about 2D deformations, for example, if this deformation and this deformation have to be in the same plane of paper, and that however you deform, you cannot lead to a lack of continuity of the material. So if you said you were to deform the material like this, for example, then in the adjacent control volume also something might deform like that, and then you will have this region which is suddenly devoid of any material. So if I were to give you the constraint that all your deformations have to be such that material continuity assumptions cannot be broken, then you will see that there are only certain type of deformations are possible, and those are, so in and that's exactly what we were discussing last time. And the first was translation. Superimposed on that, you can have another dilation, which is a scaling of this box, right? The other is angular deformation, which is nothing but shear. Okay, we'll look at each of these points in more detail. And the final was the rigid body motion. So you can show mathematically that if you give that kind of a constraint, then these are the possible deformations that you need to account for. There is actually one more deformation that is mathematically allowed, that is reflection, but reflection is not something that we have to discuss right now within the context of our course. So we will confine ourselves to these four, but mathematically there is one more that might come in. Okay, so we have to discuss these different aspects. So let's talk about translation. Okay, the first one. Okay, so translation. Translation is straightforward, right? So you have a box and it has moved to some other location. Okay, so maybe I'll just draw this with a dash that way. Okay, so this box has moved. So there is some displacement of this box that has taken place, but we are not, as we said, we are going to be concerned with rates in fluid mechanics. If you are a solid mechanics, you could just be concerned with the displacements, but in fluids, we are always concerned with rates. By the way, this is a very, very important distinction between solid and fluid mechanics, that in fluid mechanics, we are mostly interested in the rates of the deformation, whereas in solids, we are interested in the deformation itself. And this is fundamentally connected to also the control volume approach that we take, and I'd like you to think more about it. Okay, so just give it some thought. This is not a very trivial thing, but there is a reason why this strain rates are strain rates and control volumes, they sort of go together sometimes. Okay, okay. So here we have x hat, which is the displacement, but we are going to be worried about the velocity. So for translation, things are rather straightforward. I'll erase this when I have to erase it. Just a second. Okay, so the other quantity was dilation. So dilation takes place because you had a box, and that this box has now maybe grown in size. So let's say this is point A, this is point B, this is C, this is D, the vertices of the square. So this has grown to some B dash, some C dash, some D dash. Now ask yourself, why would this happen? Why would point B move to B dash? So this, if this were an infinitesimal volume where this is dx1, let's say this is one of the coordinates and I call it dx1, and we are just going to be dealing with 2 dimensions and we'll just generalize to the 3rd dimension. So if it is dx1, dx2 and so this vertex A is moving with a velocity, maybe I'll just write it with another color. So vertex A is moving with a velocity u or u1, okay, okay. So the subscripts refer to the directions, and there's a reason for that. We will discuss that. This will help us with the understanding the tensorial form easier. So you have u1 as a velocity at A, but the velocity at the vertex B is not u1, right? And that is why it is moving to B dash. So there is a difference in the velocity at this location. So what is this velocity? I can just use Taylor series approximation. Okay, this is my velocity at B, okay, plus higher order terms. So let's say I neglect all the higher order terms. Okay. So I have only this to deal with. So this change of volume due to this extra, so what is the relative velocity between point A and B? Okay, maybe I'll write that and then I'll write that, just a second. So the relative velocity, okay, between these 2 points is simply this quantity. Okay, this is dx1. So what is the change of volume that this has led to? That the fact that there is an extra velocity here which is changing the volume, dx1. Okay, so this is the linear, and then you have to multiply it with the area. So I have to include the other dimensions, x2, x3. And then you have, so this is the total change. So I just have to multiply it with the dt to get the third one, right? So this is for the simple case of 2 dimensions, right? So this is, let's say, the contribution of 1. So in the more generalized sense, if I have to write this, then I will say that my net, actually it's a good time to get rid of this as well. So my total dV, due to all these factors, you can see that it's rather straightforward, right? If you try to generalize. And then you have dx1, dx2, dx3, dt. So now my volumetric change, which, let's say, if I were to define it as theta, I would have, this is my volumetric change. But we have said before that we are going to be dealing with rates, right? So we are going to be interested in theta dot, and the theta dot would be 1 by v dv dt. Okay? This is my rate of volumetric change. So what is my theta dot? See, this volume, this is the volume of the infinitesimal element, right? And this dt can cross with that. So this is nothing but does this remind you of something? We had been looking at some of these good the tensors and vectors in some of the earlier classes. So hopefully you remember some of those mathematical preliminaries. Does this remind you of something? This is equal to, if I had to write it in vector form, it would be this, right? So we had dealt with incompressible flows. And what did we say happens to this quantity for an incompressible flow? It's equal to 0. So for an incompressible flow, this volumetric rate of change is 0, right? Okay. So you see how things are falling into place? Just 1 second. Okay, so I hope you have taken this down. I can erase this from the board. So what I'll do here, I will okay, so we have done translation, which is this we have done dilation. The theta dot is something, this quantity. Now comes angular deformation. Or shear. And this is just another fundamental way in which materials can deform. And what happens in this case? So if you have a box, then due to shear, okay, this is not a good drawing. Yeah. So the angle between these two lines does not remain at 90 degree anymore, and it has changed. In this case, an acute angle, right? I mean, this is the standard way to draw it. And let's say this angle now is d alpha. All my quantities are still the same. This is dx1, okay, this is dx2. So this is, let's say, another angle, d beta. So y has, so this here, this is again point A, and this is again point B, and you had velocity u1 here at A, and at B there is some difference in velocity because of which this point B has moved here, right, in this direction. So what is this velocity, right? So what is this change? So you again have u1 plus, okay, so sorry, okay, wait a second. Okay, so this change now, so you had, this direction is 2 actually, so I'm making a mistake. So this is u2, and here you have u2 plus del u2 by del x1 into dx1. So this is, this length is equal to this into dt. Okay, so this length is this quantity multiplied by another dt. So what is my tangent of d alpha? So my tangent of d alpha is simply this quantity here, del u2 del x1 into dt, which implies my d alpha is equal to, assuming very small deformation, so that tan d alpha equal to d alpha. Right? Okay, so I've taken care of this particular angle. What about beta? If you look at it, it is simply this 2 are getting reversed over there. Okay, so I want you to do it yourself, and this is what you should get. Sorry, there's a dt here. Right? So if I had to deal with the rates of change of alpha and beta, so I'm not, because this is again fluid mechanics, I'm dealing with rates. So this d alpha this is now equal to del u2 del x1 plus del u1 by del x2. Okay, fantastic. So this is an important result. So what I will do now is I will define a quantity, And I always tend to make sure that I need to check the name of this. So if I have to define my rate of angular deformation, right? So this is my rate of angular deformation. So now I define my rate of angular deformation. I am going to define it, okay. So this quantity, I am going to name it as S12, and I am going to define it as an average of this change of the angles. So there are two angles that are changing, so I am just going to define it as a half of d alpha dt plus d beta by dt, which is equal to del u2 del x1 plus del u1 del x2. Right. So does this is obviously the deformation that is happening in this two-dimensional plane, but there are deformations happening in the other one. So you can now write easily, I mean, I'm just going to write one more, and you know how this will look like. Right? You can define all the cross terms this way. Now, okay, now what I can do is I can create a matrix. See, I hope you see why I chose 1, 3, 1 and all that instead of x, y for the coordinate system, right? And that's because I'm going to equate it to a 3 cross 3 matrix, where here I now need, so I have all the cross terms with regards to the angular deformation. I have S12, S13, S21, S23, all those cross terms I have, which are going to reflect my rate of angular deformation. And what about the non-cross terms, which are S11, let's say I want to define a new matrix here, and this quantity S, I could define the diagonal terms as okay, this is a 3 cross 3 matrix. And here, of course, I have S12, S13 from here, right? And this. Yeah. Sorry. Right? I can define a matrix like this, and this matrix is now called, okay, again, this is called the shearing rate tensor. Okay. This is called, I want to make sure I'm getting the name right, that's why, shearing rate tensor. And the shearing rate tensor takes into account my dilation as well as the rate of angular deformation. Okay, so I'm here now, I am ready to rate right? And these are the terms of the matrices. So Sij are the ith and the jth term, and if you put ii, then this just becomes the dilation, right? So the trace of the shearing rate tensor, by the way, I hope you know what the trace is. Trace for any matrix is the sum of the diagonal elements. Okay, so the trace of Sij, let me write it with this one. Okay, so trace of Sij, which is basically summation of Sii. So Si's, or if you don't want, okay, so I'll just, till now I'm not using the tensor notation yet, so I'll just pretend these are the matrix values. So this is simply this quantity, right? So now I've been able to combine my angular, the shear that's happening, and my dilation into one important tensor. Okay, this is a rather important tensor for us to deal with. Okay. So I hope I have explained this well. Okay. So just a second, I hope I'm not missing out anything. Oh yes, okay, there's one more thing that you should note, and I hope, yeah, there's some space. Okay, so note Sij is a symmetric matrix. Sij is symmetric. Okay, that's it. So that is Sij equal to Sgi. So the way you have defined it, you have automatically achieved this. Okay, this just comes from the way we have defined all the important quantities. Okay, that leaves us with the last bit, which is rigid body motion, rigid body rotation, right? So we have looked at translation and the other rigid body motion. So translation is a rigid body motion, and the other rigid body motion possible is simply rotation. Okay, so this entire body has, if this is the axis, z axis coming out of the plane of paper, this entire square has rotated along this axis. Okay, and this angle, we will still say this is d alpha, this is d beta, and we will define once again the rate of rigid body rotation as an average of all these quantities. Okay, so we are just going to define it like that for our system. So if you look, so what did we get for d alpha? So last time when we were doing this, d alpha dt, we got this quantity, right? And once again we will have d beta by dt, but this time what has happened is the displacement has now occurred in this direction. If you try to recall with the previous diagram, right, this point had moved in this direction, in the positive direction. But this time, this motion of this vertex now is in the negative direction. But the rest of the quantities, they all remain the same. I mean, what is causing this vertex to move away? The derivation and all that remains exactly the same. So all I have to do is this now. So if I have to define an average rotation rate, this is some rotation rate, then it is del u2 del x1 minus del u1 del x2. Right? And if you had to define the other ones, how would you do it? So if you try to do this, and please, I just have limited time, so I cannot go into deriving all the details for this. Sorry, my feet are stuck. Sorry. So I cannot go into details of deriving each of these for you, but you should not try to memorize this, but just you should derive it yourself for your own sake. And what you will find is this will become now. I did not do this from memory. Okay, I think these terms are all correct. I'm just going to quickly double check. So 2 is, yeah, this is correct. So 1 is del u3, right? Okay, so all these terms are correct, and I wasn't trying to do this from memory. All you have to do is to realize that now there is a vector. Okay, so if you were to look at this in the vector form, this quantity is nothing but this quantity. Okay, and this is also called the rotation rate vector. Okay, yeah. Oops. Okay, sorry. Okay, I am sorry. This is now I am tripping over my rotation rate vector. And this now, so in a sense we have finished the final deformation of your infinitesimal volume. So these are all infinitesimal, remember. So these are dx1. So if you had to look at this definition, look at these, look at this control volume, then you will just be, sorry, these are not control volumes, these are fluid particles, and their deformation, we have covered all of them, and finally the rotation which comes out, which is given by the rotation rate vector. Okay, and this is defined as half delta nabla cross u. So this is now cross product, and that is why these come like this. So here you can sort of, if you do this cross product, you should come up with all these different terms. Now in fluid mechanics we have something called vorticity. Okay, and we define, so in fluid mechanics we define vorticity as twice of this quantity. So this is simply this cross product. And for irrotational flows, and we define rotational, we will come to this in a later chapter. For irrotational flows, this is equal to 0. And for rotational flows, obviously this quantity is not equal to 0. Right? So we have dealt with all these different motions, and we have been finding the different quantities which will help us evaluate these deformations, and that's the trick. Okay. So I will stop here now, and I'll record the second part on the tablet. Okay. So we'll stop here.